Hello there, Algebras. Welcome to your Chapter 12 Lesson 2 notes on graphing exponential functions. Now, we did talk about graphing exponential functions back in Chapter 3 when we were learning how to graph every type of function, and we were relying solely on the graphing calculator to get us to the graphs of the functions. So matching y's for our inputs in x and talking about that. We talked about the general shapes of these functions. Now, yesterday we kind of reviewed what that looks like. And so if we are considering the general shapes of our exponential functions, exponential growth functions are very rapid increases, while exponential decay functions are very rapid decreases. And so these like rapidly increasing or rapidly decreasing curves are what we use to talk about exponentials. What we'll do today is we will graph the two most basic exponential growth and decay functions, and then we'll compare those with some slight changes to the function equations. And we'll learn from that how we know an initial amount, which we also call a y-intercept, how we determine what the base kind of determines for our matching y values with our x inputs, and then, of course, the value of the asymptote. So how to figure out what the asymptote will give us, okay, and where that would lie on the graph. Because as we know, these are rapid increases and rapid decreases towards or away from some invisible barrier that we cannot touch or cross. That would be that asymptote that we are trying so hard to get to but can't. And asymptotes are always horizontal with our exponential functions, so they'll always be in y equals for our asymptote. Oops. We'll do ASY, not ASP. Okay? So now what I want to do is I want to look specifically at the exponential growth function to start. Okay, so I'll start with the exponential growth function. The most very basic exponential growth function we're going to use is y equals 2 to the x power. Now, this is also the exponential growth function that we used back in chapter 3 and kind of like didn't do a lot of expanding away from. But when we are graphing an exponential growth function, we'll notice that our base of our exponent is a value that is greater than 1. So notice in this case, we have a whole number value of 2. Any of these values that are greater than 1 are going to lead to a growth function when it's in the base. So in order to graph y equals x squared in our graphing calculator, the first thing that we need to do, let me get this all squared away. The first thing that we need to do is press y equals, and then we need to type our base first, which of course is a 2. Now, if I want x in the exponent, or anything in the exponent for that matter, we press this caret button that is directly above the division sign, and then we can put our x up in the exponent. Anything else we need to put up in the exponent as well. Now, I want to turn on my graph table mode because I, of course, just reset the RAM on my graphing calculator, so I need to turn on graph table if I want to see both at the same time. If I press graph, now I am seeing both at the same time. And if you look at the y-axis, or excuse me, the x-axis, this y equals 0 line, it does look like I'm touching that value all the way down here, and then boom, shooting right on up. Now, it does turn out, if I press second in graph and I'm on the table itself, here's my y-intercept value, 0, 1. If I look in the negatives just a little ways, I am getting close to 0, but I'm not actually on 0. And that is the asymptote. Y equals 0 ends up being our asymptote because I'm trying to touch 0, but I can't. Well, I also really can't on a regular grid. I really can't graph things like -5, 0.03125. That's just not something that's going to like fit on a 10 by 10 grid, or excuse me, I don't even have a 10 by 10 grid, but like a regular grid that we're looking at. So I'm going to kind of center things a little bit more this direction. I also know that 532 not going to fit on this grid that goes all the way up to 20. You'll notice that on purpose, my grid does not go into negative y values. That's because I don't have any negative y values. If my asymptote is y equals 0, I actually won't have any negative y values because this is my invisible barrier that my graph cannot touch or cross. Right here, there's my invisible barrier that my graph cannot touch or cross. So ASY, my asymptote is y equals 0. I will not be touching or crossing 0. All right, well, let's get some points we can actually graph. I'm going to start with kind of putting the y-intercept in the middle, 0, 1. And then notice I also have here, I'll actually arrow onto it so you can see it. So 0, 1, okay? And then I also have 1, 2. 2, 4. Ooh. 3, 8. Sorry, I didn't write down 2, 4. And here's 3, 8. And this will actually fit on the graph because we go all the way up to 20. 4, 16. Now, it doesn't fit on this 10 by 10 grid on my graphing calculator screen currently, but it is going to fit here because I can go all the way up to 20 on this particular graph, just based on what it looks like. So that's so interesting. Look at what those y's did. They went from 1 to 2, 2 to 4, 4 to 8, 8 to 16. So what was happening? Well, I added 1, and then I added 2, and then I added 4, and then I added 8. What was I doing? What's going on? I'm doubling my y each time. That's so interesting. Y's doubling, right? Well, what was my base? My base was 2. What is my base telling me is going to happen with my y's? They are multiplying by 2 because it's 2 raised to this power. So it's 2 raised to the second power. Oh, excuse me, right here. 2 raised to the second power, well, that's 4 because 2 times 2 is 4. And if 2 is raised to the third power, 2 times 2 times 2 is 8. And if 2 is raised to the fourth power, 2 times 2 times 2 times 2 is 16. That's where it's coming from. So let's think about what those negative exponents, so 2 raised to some negative powers, are actually doing. And let's head over here to negative 1.5. So negative 1, comma, 0.5. Think of 0.5 as 1/2. Oh, so if I had started here, if I'm doubling 1/2, that's where I get 1. Oh, and then I double that to get 2, and then I double that to get 4. Interesting. So then if we're heading kind of backwards in this function, let's go back a step and think about negative 2.25. Well, that's the same as 1/4. Okay, interesting. Now let's go back one more and figure out what 0.125 is. So negative 3.125. So let's say I didn't know what this fraction was. If I press second in mode and get back out to my home screen and I type in 0.125 and then press math and enter, my graphing calculator will turn this into a fraction so I can think about what its denominator is. Notice this fraction is 1/8. Look at those denominators, 8, 4, 2. So those denominators, like 1/8 doubled times 1/8 plus 1/8, right, gives me 1/4. And 1/4 doubled gives me 1/2. And 1/2 doubled is 1/2. Okay, it fits the pattern of my y's doubling. Now it's a matter of actually getting those points on our graphing, on our graph on our paper from our graphing calculator. So let's zoom way in so you can really see what I'm about to do. My point -1.5. So let me just go back to the graph so that you can see each point that I'm actually going to graph here. Okay, so I'll start here. -1.5. Okay, so I go to -1 on my x, and then 0.5 is halfway between 0 and 1 on my y. So halfway between 0 and 1. That's my matching y. Now go to -2.25. Well, 0.25 is halfway between 1/2 and 0. And you can see very quickly, so -2.25, you can see very quickly, we really don't have room to put a lot of these fractional points here, because this last one that I'm going to kind of fake fit is -3.125. We know that's 1/8. Well, 1/8 is halfway between 1/4 and 0. So I'm trying to get to 0 without touching it. See that? I'm trying to get to 0 as a y value without touching it. So this is where I'm just going to put a nice straight across arrow, indicating that I know I can't cross that asymptote. So I know and you know we can't touch or cross this asymptote. We're trying to get there. We're not going to get there. And then we can zoom back out and connect. Okay, so now we can zoom back out and we can actually connect the rest of the points. And we can put an arrow up here at 416, and then I can label y equals 2 raised to the x power. And I'm just going to write down here that this is a growth function. This is an exponential growth. Okay. Let's move on to exercise 2, which is, of course, my exponential decay function. It's my most basic exponential decay function. Y equals 1/2 raised to the x power. So y equals 1/2 raised to the x power. So now let's graph this function. So in our graphing calculator, I'm going to press y equals, and actually, if you don't mind, I'm going to leave y equals 2 raised to the x power. Just arrow over to your equal sign and press enter. Notice the equal sign is no longer highlighted. And if the equal sign is no longer highlighted, that means I won't see any of the points that make up this function I'm about to type in, but I keep that old function present, okay? So I won't see any of those points. And as I type in this new function that I want to see the points for, my equal sign will become highlighted. So it will show up. I just want to do this because I want to show you the two graphs simultaneously momentarily. But for now, I want to type in y equals 1/2 raised to the x power. Well, I like to see my table of points with a lot more room on them, which means I'm going to do the old-fashioned typing in of a fraction. A fraction is just a mini division problem. My base is a fraction. So front parenthesis, 1 divided by 2, end parenthesis. That makes my base 1/2. And now what I can do to get my x and my exponent, again, press the caret button and then x so that I get that up in my exponent. Now, if I press graph, I'm going to see the graph in the table. Notice that's the exact opposite direction, but same asymptote that I was just dealing with. So I just dealt with a growth function that went the opposite way. And speaking of opposites, listen to this in a second. Let's look at our actual values of x and look at that. At -4, I'm just going to arrow up one more even. At -5, it's 32. At -4, it's 16. At -3, it's 8. Look at that. So we're inversing the matching y values there. And because we're taking half each time, notice those y values are being halved from one to the next, to the next, to the next. So of course, I'll start with -4 because I can fit -4, 16 on here. I can fit -3, 8. I can fit -2, +4. I can fit -1, +2. And then 0, 1 is my y-intercept again. Okay, so here I am. Just want to show you where I am, writing these down. And then I get to 1.5. So 1, comma, 0.5. Well, we already know that 0.5 is 1/2. And then I get to 2, and that's at 0.25. Well, we know that's 1/4. Oh, look at us this time because we're decaying or decreasing. So we're decaying, we're decreasing, we're heading down in Y value. Each time we go, we're taking half of the Y value. And look at 3, positive 3 is 0.125, which we already know to be 1/8. And again, that is pretty darn close to 0. So as we get these points on here, we'll recognize that, oh, we're heading towards that asymptote, that invisible barrier we cannot touch or cross. So here's that invisible barrier that we cannot touch or cross. Same as before, it's y equals 0. We're trying so hard to get to 0, but we can't get there. And in this case, we are in a decay function because as x increases, y decreases. So let's get these points on here. I'll start with my y-intercept 0, 1 again, same y-intercept as before. -1, 2, -2, 4, -3, 8, -4, 16. Okay, so my whole number pieces and my integer pieces that I can actually get at grid coordinates. And then we are looking at zooming in to get those decimal points on here. Okay, so we'll zoom in and we'll think to ourselves, all right, well, let me arrow back up. Oh, sorry, I was in the right spot. 1, 0.5. So again, positive 1 is my x value, 0.5 right here, halfway between 1 and 0. And then 2, 0.25, well, 1/4, 0.25, halfway between 1/2 and 0. So here I am trying to get to 0. And then 3, 1/8, well, that's 0.125. And look at that, I'm getting there. And the thing is, I need to be very careful because I can't actually touch 0. So right here, that's plenty. Let's put a nice straight arrow to indicate that we know we can't cross that asymptote, but we're trying to. We're trying real hard to get there, but we know we cannot touch or cross that asymptote, that invisible barrier. Okay, it's like a shield, basically. So now let's connect the rest. I write right-handed, so let's put that graphing calculator over on the side, shall we? Okay, and arrows at the top, and then let's do the label. Y equals 1/2 raised to the x power. I tend to put my, if my base is a fraction, I tend to put it in parentheses and then put my exponent up here. Okay. Now this time, we know the y's were halving as x increased, y was halving, being taken in half. And that's the pattern we see. Growth as x increases, y increases. Decay as x increases, y decreases. So let's break down what we just saw happening here. Each function above has a y-intercept of 0, positive 1, and an asymptote of y equals 0, both of them. Okay. That's because we used the most basic exponential growth and exponential decay functions. And in fact, if you go back to y equals, and you notice your cursor is right on the 2 in y1, arrow left, so you're on the equal sign, and press enter so that it's highlighted. Now both of these functions are going to show up on your graph. So if you press second in graph, you can see them both at the same time. Okay, so we can see both of these functions at the same time, and notice that for both of these functions, 0, 1 is that y-intercept. Okay, and literally inversed the directions that we're going, but both of them are headed towards y equals 0. They're just not going to actually touch or cross y equals 0. Okay, so that's what's happening there. All right, if the base of the exponential function is greater than 1, then the function increases. That's growth. If the base of the function is between 0 and 1, then the function decreases, and that is what we call decay. Decay, decline, depreciates, decreases, those are all the getting smaller words. Okay. That is some of the very basic pieces of our exponential functions. Now, like I said, these were the most basic 2 exponential growth and decay functions. Notice they didn't have, in either of these function equations, they didn't have an a value and they didn't have a c value. If we think about the general form of what happens in an exponential function, the base is telling us what is the basics of what's going on, being raised to that exponent. The c at the very end, anything added or subtracted at the end, tells me where my asymptote is. And since both of these have 0 being added to the end, well, both of these asymptotes are y equals 0. So y equals whatever this c value is being added or subtracted at the end of the equation. The a value gives us the initial amount. Now, in both of our cases, the real front, the a value of each of these function equations is a 1. And hey, where was our y-intercept? 1. So that's how I can interpret from that basic exponential function equation where my actual graph is going to go. Is it increasing or decreasing? Where is the y-intercept? And where is the asymptote? And like I said, remember, the asymptotes are always going to be horizontal. So they're always going to be y equals equations, right? This is kind of the opposite of axis of symmetries in quadratic functions. Axis of symmetries in quadratic functions are always vertical. Asymptotes in exponential functions are always horizontal. Okay, so they're always y equals. So now I want to compare and contrast, and this is part of why I kept my y1 with my x to the second power. I want to compare and contrast if I change a values. And so that's what I'm going to focus in on today, is if I change a values, how does that look in my exponential functions? Okay, so what I'm just going to do is I'm just going to re-explain what y equals x squared looked like. So again, this function, a basic exponential growth function with an asymptote at y equals 0. Okay, so basic exponential growth. I want to go into y equals, I want to turn that off for the moment, arrow down to y2 and get rid of that. Get rid of that for a second. And what I'm going to do is plug in y equals 5 raised to the 2 to the x power, and y equals -3 times 2 to the x power. And I want to see what those two separate pieces are going to look like. Okay. Actually, let's head down to y5 because I'm going to use green for this next one. This is 5 times 2 raised to the x power, arrow right out of the exponent, and then put your end parenthesis. And remember, to get to an exponent, we want to use the caret that's right above division. So I'm only going to see the 5 times 2 to the x power when I press graph right now. But you will see from this, the asymptote is still the same, but a lot of other things have really changed. So I'm on the graph right now and I'm on -6 as an x value. But if I kind of arrow down, you can see, oh boy, I do not have the same y-intercept. What happened to my y-intercept? Well, it's 0, 5. Okay. As I'm arrowing 1, then 10, 2, then 20. Oh, it's like the last point I'm going to be able to fit. My asymptote remained the same because I didn't add or subtract anything on the end. However, my y-intercept is now a 0, 5. My 1, is 2 raised to the x power, then times 5. Okay, well, that gives me 10. And my 2 is 2 raised to the 2 power, and then times 5. Well, that's 20. So look what's happening this time. I started with 5 and double from there. So now what's double 20? This answer should be 40. And look, it's 340. See that? And then this next one should be double what 40 is. And look, it is 480. So when our starting point has changed, now the effect of the doubling changes because of what I started on and then began to double. Now, I just want to go backwards a little ways because these points, obviously, I'm not going to be able to fit a lot of. I get negative 1, 2.5. And then heading back one more. Oh, I get negative 2, 1.25. Notice I'm not even into full-on decimals yet. Like now I'm finally under 1, but I am still approaching that 0. And just one more for good measure. Okay, so if I graph this, now I'm starting here at 0, 5, and then heading up from there. It's 1, 10, and then 2, 20, and that's all I can fit. That's all I can fit. Now, if I'm going backwards, it's negative 1, 2.5. Okay, so halfway between 2 and 3. And it's negative 2, 1.5. Okay, so like a quarter of the way up on 1. And then it's negative 3, 6.25, so a little above half. And 0.3, okay, so about a third of the way. And that's where I'm going to put my arrow, showing that I would not touch or cross that asymptote. Notice that asymptote still the same. Y equals 0 because we did not add anything or subtract anything from the end of the equation. Which means that you can already predict on this other one that y equals 0 is going to be the asymptote. Now you'll notice I used a very different looking graph for this one, but I do want to show you that this is going to be the asymptote, just like it was on the previous two. And so if I press y equals, and you know what, this time I'm going to delete this, but I'm going to arrow down to y6 so I have a nice colorful one. In y6, I want to type negative 3, and then it's 2 raised to the x power. Arrow right out of your exponent and then drop your end parenthesis in order to see this. And now, this time, actually, let's press graph in. What on earth happened? The negative in the front, the negative a value, flipped everything upside down. And so when I'm on second in graph and I'm looking at these points, look at these points. 0, negative 3 is my y-intercept. And that's the a value. There it is. Right? There it is. That's the a value. So the a value is telling me there is my y-intercept. Okay? Now we also have 1, negative 6, which of course is the last point that I'm going to be able to fit as far as integers go on this particular graph. But if you look at the rest, negative 12, negative 24, negative 48. What are we doing? Just from a starting point of negative 3, we are doubling. We're multiplying by 2, hence the base. Now, if I go backwards just a little bit, because that's all I have time for, I've got a negative 1.5. I've got a negative 0.75, 3/4, right? I've got a negative 3.75, 0.375, excuse me about that, negative 3.75, negative 0.375. And think about those backwards. Negative 1, negative 1.5, negative 2, negative 0.75, negative 3. Look at that. We're still trying to get to 0, but we're on the negative end trying to get to 0. Okay, so that is totally different from how we saw these before. Okay, so that A value is determining my starting point, and that base determines what I do from my starting point. Now, just real quick, when x equals 0, this is your y-intercept. So in each of these cases, 2 to the 0 power is 1. So what happens in the basic exponential function? My y-intercept is 0, 1. What happens here? Well, you still got 5, even though it's 2 to the 0 power. So it's 5 times 1, which is 5. And that's what makes my y-intercept in this case 0, 5. And of course, last but not least, it is still 2 to the 0 power, and then we're multiplying by negative 3. So it's negative 3 times positive 1, giving me that A value, and that A value telling me my y-intercept. So today we focused in on what makes one of my functions growth versus decay, and changing our A value to change our y-intercept, our starting point, and then the base does the rest from there. So notice we did not change our asymptotes at all today. It's just not going to be the case right now. We'll change kind of one thing at a time when we're looking at these functions, but you can see how we know we have growth versus how we know we have decay. All right, my fine friends, I will see you for growth and decay formulas when we are doing interest. So if you want to check that out next, that would be great. Let me know if you have any questions as we go, and I will see you very soon. Bye, algebras.